In this video, I want to introduce the concept of how to handle pulleys, which is something that kind of naturally goes under the heading of tension forces, because when you have tension forces, you often have ropes and pulleys involved in the problem as well. So what do you do if you see a pulley in a problem? For now, for a while in the course, we're going to assume that pulleys themselves have no mass, or negligible mass, if you prefer to think of it that way. We'll explain the reason why we have to assume that they have no mass a little bit later on in the course, but let me just give you the conclusion of that. As long as your pulleys have no mass, the tension force magnitude is the same on both sides of the pulley. So as a result, pulleys basically just redirect the tension force, so to speak. They change the direction that the rope is pointing, but they don't change the magnitude of the tension in the rope. So pulleys are basically a way to redirect tension forces into new directions so that you can use them for various things. Let me show you one simple and very famous example of a problem involving these massless pulleys. There's a device called an Atwood machine, which consists of, switch my pen color. There's a device called an Atwood machine, which involves a pulley. So this circle is the pulley. And then we have a rope, which goes over the pulley. So we have a rope hanging down from both sides like that. And then we have a block hanging from each side like this. And the blocks have different mass. And so, of course, as you can guess, what's going to happen if you release this thing from rest is the heavier block is going to fall and the lighter block is going to rise. So let's say for our example here, let's make this one a 10 kg block. And let's make this one here a 5 kg block. And then let's say that we release this thing from rest. The pulley is massless and held stationary where it is, and the blocks start to move as a result of this. What will be the acceleration of the blocks is my question. So, step one, as always, free body diagram. I think I'm going to draw my free body diagrams off to the side because I don't want them to get too cluttered up with the drawing. So let me redraw my two blocks down here where I have a little bit more space and draw the forces in down there. So of course we're going to have gravitational force on both blocks. So the gravitational force points downward as always. So I'm going to drop my units to save some space here, in which case this guy is going to be 5 times G from the 5 kilograms. And this guy is going to be 10 times G for 10 kilograms. So those are my gravitational forces. Now I also have tension forces. I know that the tension forces here are going to point up because the rope is pointing up. So I'm going to have a tension force up on this guy and a tension force up on this guy. And now in general, we would have to say the tension force on this guy is T1 and the tension force on this guy is T2. But since we have a massless pulley in this problem, we can assume that T1 equals T2. So really, you don't really need the subscripts. You can just call this T. So the tension in the rope is T on both sides of the pulley. The other thing I want to make special mention of here is especially when you have problems with pulleys, you often have blocks moving in different directions, maybe with the same magnitude of acceleration, but not the same direction of acceleration, as in this case, that when the blocks rise and fall, they have to rise and fall the same amount because they're connected by this rope. So as a result, they have to have the same displacement magnitude, the same velocity magnitude, and the same acceleration magnitude because their motion is exactly the same other than the fact that one is up and one is down. So you need to be very conscientious about keeping track of the direction of the acceleration vector So like in this case here, I'm guessing that the lighter block, the 5 kg block, is going to accelerate upwards, and the 10 kg block is going to accelerate downwards, but it's the same A on both of them. It's the same magnitude of acceleration, but not the same direction. I'll show you why that's important momentarily, but I highly, highly, highly encourage you to make note of the direction that you're assuming the acceleration goes, as I just did there, because otherwise the biggest mistake you can make in this problem is sign issues that come into play because you haven't been careful about the direction of the acceleration vectors. Okay, so anyways, let's move on. We have our free body diagrams. We don't need to break anything into components in this problem because there's no two-dimensional stuff. Everything's just one-dimensional in each of the two diagrams. So we still have two F equals ma equations, one for each block, but we don't need to break any vectors into components. So for the 5 kg block, the F equals ma equation is going to be, I'm going to drop the subscripts on tension again because they're equal. So it's going to be T in the positive direction, 5g in the negative direction, and then m equals ma. M is 5, and you'll note here, acceleration points in the positive direction, so I can put in positive a there. So it's T minus 5g equals 5a. For the 10 kg block, we're going to have T points upwards. I'm still making up the positive direction. And then I'm going to have 10g points downwards, and then equals ma. M is 10. But now, this is where you have to be very careful. This acceleration points downwards. If you're going to call up as the positive direction, which I did, that means you need a negative sign here because your acceleration actually points in the negative direction. So I just want to call special attention to that here. It's true for all problems, but it comes up a lot in these pulley problems where you have to make sure about whether your acceleration vector is pointing in the positive direction or the negative direction. And if it's pointing in the negative direction, you need to put a negative sign in front of it because the acceleration is a vector just like the force is a vector. So it has to get treated the same way that the forces get treated on the F side of the equation. If necessary, it has to get broken into components, and it definitely has to get signed of whether it's positive or negative. So A here represents the magnitude of the acceleration. So the variable A should turn out to be positive. Okay. Anyways, let's keep going. So there's my two F equals ma equations. You can see I have a system of two equations with two unknowns here. My unknowns are A and T. My goal is to solve for A. So let's solve one of these equations for T first so that we can substitute it out. So let's take this one here and we'll solve it as T equals 5g plus 5a. And then I'm going to substitute that result in for this T, and that'll give me 5g plus 5a minus 10g equals minus 10a. On the left-hand side of the equation, I'm going to have 5g minus 10g is negative 5g. And then let's move the 5a to the other side of the equation, and it'll be minus 15a. So then the two negative signs cancel out, and we end up getting a equals 5g over 15, which is about 3.27. And as I said, I was expecting a positive answer because I've already built all the negative signs into my directions of the vectors in the F equals ma equation. So the answer is the acceleration magnitude is 3.27 meters per square second. The left block is going up, as you can see here, and the right block is going down, as you can see there. If you also wanted to know the magnitude of the tension force, you would just take this guy and substitute back in here and get T equals 5 times 9.8 plus 5 times 3.27. So that's going to be 5 times 9.8 plus 5 times 3.27 is about 65. Let's call it 65.4. So there's the tension force if that is required. All right, so that's how you handle pulleys. Important points are, if it's a massless pulley, tension is the same on both sides of the pulley, and make sure that in pulley problems, you're very conscious of what directions the acceleration vectors are pointing, and make sure those directions are built into your F equals ma equation somehow.